In an earlier video, we introduced components related to electricity and we defined exactly what electricity was. Now we're going to relate all of those components together and use a law, a fundamental law in electricity called Ohm's law. So for a quick review, let's just talk about what we discussed as far as the components of electricity. We have voltage. Voltage is that potential difference between the electron supply and electron shortage. We have current, the net flow of electrons through a material. Remember, when we talk about conventional current, we're looking at it from positive to negative. If we were talking about the net flow of electrons, specifically, we look at it from negative to positive. When we work these problems with Ohm's law, we're going to look at conventional current, positive to negative. And then finally, resistance, the measure of a material's opposition to the passage of electric current. So those are our three fundamental concepts that are related to electricity. We have voltage, we have current, and we have resistance. And using Ohm's law, we're going to connect those concepts together. First, let's talk about units. So units are so important when it comes to electricity. So units of current are amperes, or amps. They're represented with the capital letter A. So don't get that confused with when we represent current with the capital letter I. Symbolically, we represent current with an I. The units of current are amps, and we represent that with a capital A. But let's talk about what an amp is. So an amp is the unit of current, and current is the amount of charge passing a point per unit time. So that charge, remember, is the number of electrons, so related to electrons. And when we talk about current, as in terms of an amp, we are looking at it as the number of coulombs per second. A coulomb is a new term that we're introducing, and basically a coulomb is a grouping of electrons. Remember when we talked about the copper block? So we had this block of copper. There's so many free electrons in there, so many valence electrons in here. And so if we were to look at the actual just individual number of valence electrons passing a point over time, that would be such a huge number. And so what we do instead is we group them together in a bundle. And so we look at 6.24 times 10 to the 18 electrons, so grouped together. That might be kind of confusing to you. And so you might think about it in terms of a dozen. So when I say a dozen eggs, you immediately know that there's 12 eggs in a carton. So if I say 1 coulomb, you should immediately know that there's 6.24 times 10 to 18 electrons. It's kind of the same concept. It's just a grouping. So 1 amp is 6.24 times 10 to the 18 electrons per second, or coulomb per second. And so this is important that you remember these units, because as I mentioned in a previous video, these units are so important and they can guide you through solving the different problems. Here's a class problem for us. A battery powers a flashlight. The battery supplies a steady current of 1.3 amps over 8 minutes. So this is, if you picked up any flashlight, you could probably figure out how much current is in there, and you hold the flashlight on for 8 minutes. So this is kind of something you can visualize with us. And so how many electrons leave the negative terminal of the battery during this time period? So we have a time period of 8 minutes, and we know the current is 1.3 amps. So basically, we're trying to find the number of electrons that flow through. Okay, so if we're looking at the battery powering the flashlight, we know, so our known information, our known info is our current is 1.3 amps. Our time is 8 minutes. Okay, and what is our goal? So that's our known information. Our goal is number of electrons leaving the negative terminal, right? So that's what we're trying to find. So right now, just looking at these units, I'm kind of thinking, oh gosh, I don't even know where to start. But remember, what did we just learn about amps? Is that they break down. So if that's 1.3 amps, then I can also say that's 1.3 coulombs per second, right? And I also know other known information. I do know that there are 6.24 times 10 to the 18 electrons for every 1 coulomb. So that could be useful. And if I'm looking at my units here, I can see that I have coulombs and coulombs. I can see that I have seconds, which is a unit of time, and I have minutes. Well, I know that I can write the terms of seconds because I can relate seconds and minutes together. And then what would I be left with? Electrons. So somehow in here, I can figure out, I can work with these units to find my goal. My goal is the number of electrons. So I'm trying to find electrons. So let's write down what we know. We know that there are 1.3 coulombs per second. I also know that there are 6.24 times 10 to the 18 electrons per coulomb. I can see that if I write it like that, my coulombs cancel out, and I'm left with units of electrons per second. All I want are units of electrons. So somehow I need to get rid of these seconds. I know that this is 8 minutes, so I can say multiply this by 8 minutes. No, that doesn't get rid of my seconds, but I know that I can say 1 minute consists of 60 seconds. And now I can see that my minutes cancel out and my seconds cancel out. And you could have done that conversion earlier before writing it in your formal expression. You could have done that before. You can convert the 8 minutes into seconds. And then when you multiply it out, remember, everybody get your calculator out while I'm doing this. And I get there are 3.89 times 10 to the 21st electrons. Leaving that negative terminal of the battery, if I held that flashlight on for 8 minutes with a current of 1.3 amps, there are 3.89 times 10 to the 21 electrons. And I didn't start with an equation. I just had my information that I knew about the problem. I had 1.3 amps, but I knew that I could break down amps into a coulomb per second. So 1.3 amps is the same as 1.3 coulombs per second. And then when I have my units written like that, I was able to look ahead and think about what can I cancel out in order to get what I need for my problem. And so I was able to cancel out all the units and end with electrons. So the takeaway here is units of current are amps. An amp breaks down into coulombs per second, and a coulomb is 6.24 times 10 to the 18 electrons. It's just a grouping of electrons. Okay, so the next thing that we need to talk about is voltage. So voltage, the units of voltage are volts, so that's pretty easy to remember, and it's represented when you write down a voltage, the unit, you write it as a capital V. So remember, voltage is the potential difference between the electron supply and electron shortage. And if I formalize that a little bit more, what we're actually really measuring is the potential energy per electric charge of coulomb, or per electric charge or coulomb. So remember, the coulomb is that grouping of electrons. So we're looking at the energy per that grouping of electrons. And so energy, if you recall from maybe your high school days, units of energy are joules. And so when we talk about a volt can be broken down into a joule per coulomb. Just like an amp can be broken down into a coulomb per second, a volt, which is what we write as the unit of voltage, can then be broken down into a joule, a unit of energy per electric charge or coulomb, so a joule per coulomb. And so the final component that we need to talk about is resistance. So you can see pictured here are a bunch of resistors. These, and in my hand, I have a resistor. In your kit, you have a bunch of resistors. These are included in circuits to add that opposition to flow for various applications. So the unit for resistance is ohms, and it's represented with the Greek letter omega. Okay, so just to kind of quantify everything that we just did, we have voltage, we have current, and we have resistance. Symbolically, they're represented by V for voltage, I for current, R for resistance. That's when we write it down as an equation. So if we were writing an equation that had those components in there, we would have V, I, and R. Now the units which quantify what those values are, So if I said 15 chickens, my unit there is chickens. If I just said 15, you wouldn't know what that was. So that unit, what is that number related to? That's what we're talking about with those components. For voltage, it's volts. For current, it's amps. For resistance, it's ohms. And then just another note that you should make sure you remember, volts can be broken down into joules per coulomb. It's a unit of energy per charge. Amp can be broken down as a coulomb per second or a charge per time. So it's important to remember voltage, volts, current, amps, resistance, ohms. So before we get into exactly what's going on with current, voltage, and resistance, let's talk about circuits and quantify some things related to circuits so that when I use the terminology, you know what I'm talking about. So a circuit has to have a closed path. So in order to induce the flow of current, it has to have a closed path. So creating what we call a closed circuit causes the voltage to push those electrons to move, and it tells them where to go. Remember, the electrons have to go from negative to positive, and so when you close that path, they know that they see that path. So basically, it's kind of like the fog clears, and it knows, okay, this is where I'm going. I'm going to that positive side. So components like resistors are included along a path. So an incandescent light bulb is an example of a resistor. These physical resistors are resistors. They add resistance as that electron flows through the circuit. If we didn't have resistance there, if there was no component that was kind of stopping or in between the negative and positive side, we would have what we call a short. And then it would get really, really hot because those electrons would just immediately get to that positive side and they would burn up. It'd be too fast. So we include resistors in different ways for that purpose. And then what you're going to see throughout the quarter and beyond Engineering 120 is circuit diagrams. So it's one thing to draw a big incandescent bulb with a battery and lines connecting them. Imagine if you were doing a schematic for a house and you had to draw each and every component like that. It would get crazy big, it would get so chaotic, and it would be so hard to decipher. And so within the industry, a universal standard of diagrams, symbolic representations of components have been accepted. And so as engineers, you need to understand what the different component symbolic representations of those components look like. And so you can draw them symbolically to represent the circuit components. And so pictured here on this presentation, we have a power source, a DC power source, and we have a resistive component. And then these lines are just conductors. So as we learned earlier in a previous video, conductors allow the passage of electricity. And so the electricity can flow through the resistor and through this closed loop circuit. So just to kind of show you, reiterate that schematic representation, this is a power source. So specifically a DC power source like batteries. And you see it has a long line with a plus sign and a short line with a minus sign. Then we have resistors here. It's basically a little zigzag. And I love that that's the symbolic representation because resistance is the measure of the opposition to flow. And you can kind of see if you were current passing through this wire, you wouldn't be able to easily pass through. You'd have to slow down and do this zigzag. So I think it's a great representation of a resistor. And then a conductor. So when you build circuits on your board for your Arduino, on your breadboard, you're going to connect just wires, and we call those jumper wires. And so it's just a straight line, and that makes sense because the flow of electrons is just flowing through those conductors pretty easily. Okay, so let's talk about Ohm's law. So all of this is building up to connecting those components together: current, voltage, and resistance. And how do they relate to one another? So here's my scenario. I have a circuit here. The circuit has 5 volts power supply. It has 0.05 amps, and it has a resistance that's measuring 100 ohms. So we already talked about those units. We know that the voltage, the current, and the resistance have volts, amps, and ohms respectively. And if those are the numbers of this circuit, can you look at it and see a relationship between those values and maybe decipher what you think Ohm's law will be? If you're looking at it, you might see that if you multiply current times resistance, you'll get the value of 5. And so that is Ohm's law. So Ohm's law is current times resistance. And so when you multiply the current times the resistance, you get voltage. So when you multiply amps times ohms, that's the same thing as volts. So an amp times an ohm is a volt. And so this is Ohm's law. V equals I times R. Voltage equals current times resistance. So commit that to your memory because that's very important. You'll be using Ohm's law throughout the entirety of this quarter. Okay, let's work a problem. Let's connect this to a problem. So for a given circuit, what I want you to do is draw symbolically the circuit. I want you to label voltage, current, and resistance. And I want to assume that these are AA batteries that are pictured, and the bulb provides 12 ohms of resistance. Then I want you to determine the current delivered by the resistor and determine the number of electrons that leave the battery pack over 2 minutes. So I'm going to work this problem with you. Looking at part A, and we see that there are 1, 2, 3, 4 batteries on this bulb circuit, on this light bulb circuit. And these are AA batteries. Each one is 1.5 volts. You could draw each one individually. So you could draw it like this, and you can draw each individual voltage source kind of like this, and draw 4 of them with the plus and minus, and you can put 1.5 volts, you can put 1.5 volts, 1.5 volts, 1.5 volts, but that is a little cumbersome. What I would actually recommend you do is just write it as one singular voltage source. So you have your plus and your minus, and if they're one right after the other, this is what we call series, and we'll talk a little bit more about that terminology in another presentation. But these are in series. What we can do is just add them together. So when there's 4 batteries like this, that's going to be 6 volts total. So your voltage source is 6 volts. Then you have your incandescent light bulb, which we already said it acts as a resistor, and given to us in the problem is that it's 12 ohms. Okay, well, we haven't labeled the current, but the current's going to leave the positive and go towards the negative. We don't know the value of current, so I'm just going to represent it with an I. So let's make sure we've done everything. We labeled the voltage, current, and resistance, and the batteries are AA, which we accounted for with the 6 volts, and the bulb has 12 ohms. Determine the current delivered to the resistor. So what are we going to do in order to determine the current delivered to the resistor? We're going to use Ohm's law. So if I look at Ohm's law, I know that V equals I times R. My voltage is 6 volts. I'm trying to find my current. I don't know the value of current, but I know my resistance is 12 ohms. So if I divide by 12 ohms on both sides, I can say current is equal to 6 divided by 12, and that is 0.5. And what are my units of current? Amps. So that's my answer to part B. I've done part A, I've done part B. Now part C, we want to determine the number of electrons. So that's my goal, number of electrons. And I'll label it as goal. That's my goal. That leave the battery pack, but this time it's in 2 minutes. So instead of 8 minutes, we have 2 minutes. So we know the current. We know that there's 0.5 amps, and so this is part C. We know that the current is 0.5 amps, and we know that the time is 2 minutes. Well, we learned from the previous example, it's easier if we write it as 0.5 coulombs per second. And so when we write it as coulombs per second, that gives us a little bit more direction. So I know that this is 0.5 coulombs per second. I'm going to multiply that by the number of electrons per coulomb. So I have 6.24 times 10 to the 18 electrons for every 1 coulomb. Recall, we discussed that earlier when we broke down what a coulomb per second was and then what a coulomb was. So we can cancel out our coulombs. We're left with electrons per second, but we know that this is left on for 2 minutes. And I also know that 1 minute is 60 seconds. So now I can cancel out my minutes, cancel out my seconds, and I'm left only with electrons. So when I multiply that out, and y'all multiply it with me, I get 3.74 times 10 to the 20 electrons. So this video formalized Ohm's law. It related voltage, current, and resistance together. If we're looking at voltage and we relate it to current and resistance, we see that voltage is directly proportional to both current and resistance.